Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Existence of Solutions. That is, we'll discuss whether the solution exists or not for the case of Volterra equations from the paper Mathematical Physics. So let us see what we are going to learn in this module. In this module, we will learn about the existence of solution of Volterra equation and the examples from mathematics and physics. We start with the discussion of existence of solution. So we have already seen in previous modules that some specific integral equations can be solved using various methods. In particular, we discussed the use of integral transforms to find the solution of integral solution. The question that occurs is, does a solution, at least in principle, always exist for an arbitrary integral equation? The solution we are searching for can be either analytical or numerical. The answer to this question is negative. That is, there is no general theorem to assert that given an arbitrary integral equation, a solution always exists. Now remember, this is quite unlike the case of linear differential equations, where given that the coefficient functions are non-singular, a solution always exists. A simple example will illustrate this point. Consider, for example, the homogeneous integral equation for the unknown function f of x. A homogeneous integral equation for the unknown function fx is given by g of x is equal to integral over dx prime from a to b of the product of two functions k, which is a function of x and x prime, and f of x prime. Here gx is a given function of x, a and b are constants, and the kernel k is supposed to be given. Now, if we take the simple case of the kernel, which is separable, in the sense that the kernel k, which is a function of x and x prime, can be separated into a product of two functions, u and v, one a function of x and another a function of x prime only. Then we can write gx as, since kx is now the product of two functions, one a function of x and x prime, the x can be taken out of the integral sign, and therefore the function gx can be written as gx is equal to ux multiplied by an integral over dx prime from a to b of vx prime fx prime. Now the integral is over dx prime, and the integrand is the product of two functions, both are of x prime, and the limits are constants. Therefore the integral does not depend on x or x prime and is simply a constant. Therefore in this case of a separable kernel, gx is simply ux times c, where the constant c does not depend upon x. Now for any arbitrary u and v, obviously this last equation cannot be satisfied, and hence the solution in general does not exist for the simple case which we have taken here for the separable kernel. Let us consider a simple Volterra equation of the second kind for the unknown function f of x. So we consider the equation f of x is equal to 2x plus lambda 0 to x dx prime fx prime. Now notice that in this case, the function g of x inhomogeneous function part is simply taken to be 2x, and the kernel is simply a constant lambda. Now if lambda is much smaller than 1, then obviously the second term is much smaller than the first. Therefore in the zeroth approximation, we can write f of x is equal to 2x plus terms of order lambda. So equivalently, we can write this f of x is phi naught x plus terms of order lambda. Now we substitute this expression back into the integral equation to get f of x is equal to 2x plus lambda integral 0 to x. Now for f of x prime, we substitute 2x prime So this integral becomes 0 to x 2x prime dx prime plus terms of order lambda square, where the terms of order lambda square start with the lambda square term when written in powers of lambda. We can rewrite the last equation as f of x is equal to phi 1 of x plus terms of order lambda square, where phi 1 of x is 2x plus lambda x square. Obviously, we can continue this process to get f of x is equal to phi 2x plus terms of order lambda cube, where phi 2x is equal to 2x plus lambda square x cube by 3 is equal to, next term we can write as phi 3x plus terms of order lambda cube, where phi 3x is equal to 2x plus lambda x square plus lambda square x cube by 3 plus lambda cube x4 by 12, and so on and so forth. Finally, we can write the n terms of order lambda to the power n as f of x is equal to phi nx plus terms of order lambda to the power n plus 1, where phi nx is given by 2x plus lambda x square plus continued till you have terms of order n minus 2 in lambda. Namely, last term is 2 twice lambda to the power n minus 2 x to the power n by n factorial. So we have been able to obtain by this process terms up to order lambda to the power n. So what we do now is to let n goes to infinity. In that case, fx is an infinite series. Now it's an infinite series which is a geometric series and it can be summed. So we get f of x is equal to summation n is equal to 1 to infinity 2 into lambda to the power n minus 1 into x to the power n divided by n factorial, which can be summed, which is nothing but equal to f of x is equal to 2 by lambda multiplied by e to the power lambda x minus 1. So solution fx we are able to write in the form of a infinite series, which in the simple case we consider can be summed. The infinite series that we obtain is a series in lambda times x, and this infinite series we have summed is called the Nyman series. Now for the Volterra case, it becomes the exponential series which is convergent for all values of lambda and x. Thus, for the particular integral equation that we have just studied, we have an existence theorem. Namely, a solution exists for all values of lambda and x. The question is that we have to investigate whether this result is more general or not for the Volterra equations. Now we discuss the existence of solutions for the Volterra equations. So we start with a general inhomogeneous Volterra equation of the second kind, which can be written as f of x is equal to g of x plus lambda integral over dx prime from a to x of k, which is a function of xx prime, multiplied by f, which is a function of x prime. Now in this equation, fx is the unknown function, lambda is a constant, gx is a given function which is responsible for making the equation inhomogeneous, and so is the kernel, which is a function of two variables. Now we would like to investigate whether a solution for fx exists in the domain where x lies between x1 and x2. We assume that in this domain, the given function g of x is bounded, which means that mod gx is less than some number capital G for x lying in this domain, the x lying between x1 and x2. Similarly, we also assume that the kernel is bounded too, which means that the mod of kxx prime is less than some number k for x lying in the domain, that is x lying between x1 and x2, as well as x prime variable also lying in the same domain x1, x2. Note that to the lowest order in lambda, fx is just the first term gx. We call this approximation as fx is equal to f0x, that is the lowest order approximation, which is equal to gx. Clearly, the modulus f0x is less than the number g, which you remember was that the number when the mod gx was less than g for x lying in the domain. Using this approximate value of fx, we obtain the next approximation f1 of x, which is correct up to order lambda. That is, f1x is equal to the 0th order term gx plus lambda times an integral a to x of kxx prime gx prime dx prime, and using the bound that we put on the function g and the kernel k, we find that the mod f1x is equal to the mod of gx plus lambda times the mod of this integral a to x kxx prime gx prime dx prime, which is obviously less than the mod of gx plus lambda times the mod of integral from a to x kxx prime gx prime dx prime multiplied by the limit a, which is in turn less than the number capital G plus lambda mod into the mod of x minus a into the number k into the number g. Because remember that k, the mod of kernel is less than k, mod of the function g is less than capital G, and this integral has limit from x minus from a to x of dx prime. So we have taken the maximum value of k, maximum value of g, took it out, the integral gives me x minus a, so we take the x minus a, the integral gives me x minus a mod. So it's obviously this function f1 x mod is less than this number. We can proceed in the same manner for higher order terms in lambda. For example, let us look at f2x. So f2x mod then is equal to mod of gx plus mod of lambda multiplied by the integral from a to x over dx prime of the integrand being the kernel k xx prime and f1x prime. Now f1x prime, a bound on f1x prime we have obtained earlier. So a bound on f2x can be seen to be that f2x mod is less than the number g plus lambda times the number k into the number g into the mod of x minus a plus lambda square mod into x minus a whole square by 2 into the number g into the number k square. Continuing this way, the bound on the nth approximant fnx, which is the correct fx up to order lambda to the power n, if fx is expanded in powers of lambda. It can be easily read out on the pattern of the bounds of f1 and f2. We can then see that by inspection from the bounds obtained on f1 and f2, the bound on the general term, the nth term fnx, can be written as the bound on the mod fnx is less than or equal to the number g plus the mod of lambda into the number k into the number g into mod of x minus a plus lambda square into mod of x minus a whole square by 2 into the number g into the number k square, so on and so forth till reach the nth term, which will be mod of lambda to the power n divided by n factorial multiplied by the number g multiplied by the number k to the power n multiplied by the mod of x minus a to the power n. The factor g is common to all terms, and the series for the bounds is of the exponential type. So if we take out the term g away, then this is a series of the exponential type. Hence the series converges for all values of lambda. Hence we have proved that a solution of the Volterra equation of the second kind always exists. This is an important result we have proved, that a solution of the Volterra equation of the second kind always exists. Now we consider Volterra equation of the first kind. Under some simple circumstances, Volterra equations of the first kind can be converted into an equation of the second kind, and we already proved that a Volterra equation of the second kind always has a solution. Once that can be done, the above analysis ensures the existence of a solution of the Volterra equation of the first kind as well. So if we are able to convert a Volterra equation of the first kind into a Volterra equation of the second kind, then we are assured of the existence of the solution. So let us consider a Volterra equation of the first kind, namely g of x is equal to integral a to the x over dx prime, the integrand being the kernel, a function of x and x prime, and multiplied by a function of x prime, where as before fx is the unknown function and gx and the kernel are given. Differentiating this, we get g prime x is equal to kernel of x f of x plus integral a to x k1, a function of x and x prime, f of x prime dx prime, where k1, which is a function of x and x prime, is nothing but the partial derivative of k with respect to x. So written in this form, we can see that this is a Volterra equation of the second kind if the kernel k x is not equal to 0. So if in the Volterra equation of the first kind, the kernel is such that its dependence on the two variables, when the two variables are equal, the kernel is non-vanishing. In effect then, we have the result that solution exists always for both types of Volterra equation subject to the condition that the function gx is derivative g prime x and the kernel k xx prime are bounded. We also note that the condition k xx not equal to 0 is not very restrictive. In case k xx is equal to 0, the last equation is again of the first kind. Now we can differentiate again to get an equation of the second kind with the kernel k xx prime replaced by k1 xx prime. Correspondingly, we have an equation of the second kind, provided of course the kernel k1 xx is not equal to 0. We can continue this process till we land up with a proper equation of the second kind. Let's talk about homogeneous Volterra equation. If gx is equal to 0, we have a homogeneous equation and the analysis is based on expansion in powers of lambda no longer applies. That is, if we have a homogeneous equation, then the expansion in powers of lambda no longer applies because there is no term with which you can compare lambda. So we do not analyze the homogeneous equation here. We note that if we define the kernel k bar k xx prime is equal to k xx prime if x prime is less than x and equal to 0 if x prime is greater than x, then we can rewrite Volterra equation as 0 is equal to fx plus lambda 0 to infinity k bar xx prime fx prime dx prime integral from 0 to infinity. This is a homogeneous Fredholm equation. In the next section, we will do a detailed analysis on such equations. For the kernel arising out of a Volterra equation, the fact that the kernel xx prime is equal to 0 for x prime greater than x makes a difference. We turn now to the existence theorem of Fredholm equations parallel to the analysis of Volterra equations that we have discussed in this section. So students, let us summarize what we have learned in this module. We have learned in this module about the existence of solutions for Volterra equations. We have established the solution of the Volterra equation of the second kind exists. We have seen that under some simple circumstances, Volterra equation of the first kind can be converted into an equation of the second kind. And once that is done, the above analysis ensures the existence of solution of Volterra equations of the first kind exists as well. Thank you.